Hey everyone, just finished watching the news. Now we're ready to draw some network diagrams. So there's a couple parts of this that seem a little bit easy at first, and they kind of get a little bit more detailed as we'll go. So I'll try to take my time and go at a good pace so that it kind of makes sense. First thing we need to talk about are connected graphs. So when we talk about network diagrams, the first concept we'll discuss, connected graphs. Don't forget, another word for diagram is a graph. And connected graphs have every vertex connected to other vertices. Sorry if that's a little messy, it's just hard on my phone. Phone just works way better for writing. My iPad is just not cutting it right now. Okay. So let me show you an example. So if I gave you this little diagram right here, there's a vertex, we'll call it A. There's B. Over here there's C. And finally there's D. We'll connect C and D like that. There we go. So there's your diagram. If I gave you this diagram and asked you if it was connected, is it possible, for example, to get from A to D? Yes, it is. You can get to A to D by going through B and then over to C and then down to D. Oh, you could go over from A straight through B and down to D. So yeah, it would be possible. That would be a connected diagram. Yay, it is connected. Another example that I could give you, just let me add another page. So I'll just draw you another quick example here. Draw this one right here. There's our vertices. A, B, C, D, and E. And I'd ask you, is this a connected network diagram? And it is not. You can't go from A to D, for example. It's just not possible. So this is a not connected diagram. I actually saw an article in the newspaper or on the internet today about network diagrams and the coronavirus spread, and how by disconnecting networks they're trying to help reduce the spread. So it's helping reduce these connections between people. We're trying to reduce the spread. So it's a really interesting article about connecting network diagrams and exponential growth. Anyways, I quickly digress. I'm going to pause for a second, add another diagram, and then I'm going to come back. Alright, so here's another example where I could ask you, is this a connected diagram? So take a second and try to figure out if you can get from one vertex to another vertex. Make sure you can visit all the vertices. Alright, I paused for a second, assuming you'd pause your video. So if I was here at A, I could go from A to B, no problem, because they're connected. And I could go from A to F, no problem. Or from B to E, or from, A through E to B, no problem. But if I actually get from A to C, how could you do that? Is there a direct connection from A to C? Go like this from C to D. Or you can go like this from C to D. There's actually no way to get from A to C. There's no node or vertex here in the middle that connect these edges. So these edges are not connected by a vertex, and as a result, there's no way to get from A over to C. You just can't do it. No matter which way you kind of go at it, you can't get to C. So this would be an example of a not connected network. So I hope that helps illustrate a not connected network. That's supposed to be a K, not a D. There we go. Alright, so next concept that I want to talk about is isomorphic graphs. In isomorphic graphs, There are different looking graphs that have the same info. So let me just change my pen so I can write that. They are different looking graphs that have the same information. That's not too messy for you. The graphs, you can also call them equivalent, but they're usually called isomorphic. So I'm just going to take a second and I'm going to insert 3 examples from your textbook, and then we'll go through how you can determine if they are isomorphic. Alright, so if I asked you to determine if these 3 graphs or diagrams were isomorphic, what I would do to start is I'm just going to take a second. I'm going to try to split this up into 3 parts. So the first thing I would look at is I'd look at the number of edges and the vertices for both. So the number of edges, there we go, the number of edges. So let's count the number of edges. 1, 2, 3, 4, 5 for this one. The number of edges for this one, I have a bit more room so I can write it out. Number of edges, here we go. 1, 2, 3, 4, 5. And the number of edges, I'm just going to write it as an E again. 1 up at the top, so 1, 2, 3, 4, 5 edges. Okay, so they all have 5 edges. Now let's check our vertices, number of vertices, and our number of vertices, V-E-R-T-I-C-E-S, number of vertices. So I'll take a second, I'll just switch out my color pen so it might be a bit easier to kind of do. So number of vertices here, 1, 2, 3, 4. 1, 2, 3, 4. Just can't circle because it's behind, but there's 1 up there for 4. Alright, and on this diagram here, just have to be careful because it's the top hand corner of my screen. So A would be 1 vertice, B would be 2 vertices, C would be 3, and D would be 4. So I have 4 vertices. The next thing we can then compare, so we have all the same number of edges and vertices, but you can actually go a little bit further in comparison. So we're going to see the amount of degrees, and so you'd write it as DEG bracket A. So I'm going to see the amount of degrees that A has. So you count the amount of lines, or sorry, edges that connect to A, and that's 2. Next I'll check my degrees for B. I count the amount of degrees leading, or sorry, edges leading away from B, and that is also 2. I check my degrees. Sorry, my tools are just kind of around here, so I just got to be careful. It's going to get tricky for me. The degrees for C, I count the amount of edges connecting to C. 1, 2, 3 edges, so C would be 3. And then I check my degrees. I can't even write it in just because I have a lot of tools over there, so I'm sorry if I can't fit that in, but I check my amount of degrees for D is also equal to 3. All right, so let's repeat this to see if it's still true. So first we check our degrees for A, and for A it's 1, 2, so it would be 2. Same as before. My degrees for B, that doesn't look like a B, that's better. For B, it's 1, 2 as well. Degrees for C, again, my tools are going to start to get in the way here, so I'm sorry if I can't do this well, but I can count for C. 1, 2, 3 for C. And my degrees, D, E, G, for D would be 3 as well. So you can see everything's matching between our first and our second example. So let's try, I'll just kind of do that. My degrees for A is 2. My degrees for B is also 2 still. 1, 2 edges leading away from B. My degrees for C, if I look quickly here, is 3. And my degrees for D is also 3. So because that's 3, so because our number of edges, our number of vertices, and our degrees for each of our vertices are all the same throughout, these are isomorphic. Sorry if I flipped ahead to the next slide. A little quick there, but I just wanted to, I just accidentally brushed that. So that would be a good example. There's another example in your textbook that I'll just run through real quick. Boom, magical things appear. All right, so now what we'll do is we'll first figure out our number of edges. So number of edges. Oh, come on, please. My number of edges. So this one, 1, 2, 1, 2, 3, 4, 5, 6, 7. Edges is 7. So that's good. And you're going to go across and you're going to make sure to check all this for each single one of these. So that way you can make sure that it's looking good as you go, because you're going to be using this as, like, make sure that you're doing it correct when you first start. And it'll kind of keep you going. So the next thing I'll do is, let's check this one. 1, 2, 3, 4, 5, 6, 7 edges. Whew. 1, 2, 3, 4, 5, 6, 7 edges equals 7. And let me switch close. I'm noticing the red with the red is a little tricky to keep track of. 1 edge, 2, 3, 4, 5, 6, 7 edges. Edges equals 7. All right, look, we'll go backwards. A, B, C, D, E. So that would be 5 vertices. A, B, C, D, E. So that would be 5 vertices. A, B, C, D, E would be 5 vertices, and this would also have 5 vertices. All right, so let's figure out our number of degrees for A. So we are going to do that all the way across. So our degrees for A, I'll go all the way across. So A and I'll use green for our degrees just to kind of make it a little bit easier to see. This one, A has 1, 2, 3 degrees. So for A, it is 3. And this one, it's 1, 2, 3. And for this one, it's 1, 2, 3. Sorry if I did 4 dots. That's degrees equals 3 for A. A for this one is 1, 2, 3. So there we go. Our degrees for the first one are all the same. So we're good so far. Let's go to B now for number of degrees. Our second one, I have 1, 2, 3 for B. I've got 1, 2, 3 for B. The number of degrees. For B, I've got 1, 2, dun dun dun. And it looks like B is not the same here. Let's just double check it over here. 1, 2, 3. And so that would be 3. And I'm fairly sure from looking at the textbook as well. If you take a second and you look, as you kind of move through, I believe you can kind of look through the example, and I believe that it says that basically this one is not a similar one because it's example for B is not the same. It's not doesn't have the same number of degrees for all of its vertices. And if you think about it this way, if you wanted to get from B to something like B to D, here you'd have to go through like from B. Now let me get my laser pointer so it's easier. So if you want to get from B here to D, so you'd have to go B, C, and then D, which is fine. And then if you want to get B, it's B, C, D, which is fine. If you wanted to get from B to E, let's look at that example. So B to get to E, you have to go C, E. From here, you'd have to go C, E. Oh, wait, you can go straight from B to E. So there's no direct path from B to E, and that would be one of the big reasons why it's not the same. So here, you can go directly from B to E, and here there's no direct path from B to E, and that's why these are not isomorphic. All right, so sometimes you might be asked to draw a network diagram from a map. I've had to work out on my geography skills in this unit. So what you're suggested to do, here's a map of Australia. We're going to try to make a network map, and I'm going to try my best here. Please forgive any pronunciation issues, but we'll start over here at Perth. So I'll draw Perth kind of right here. We'll stick Darwin right up here. Next we'll go over to Brisbane. Not bad. And down here is Sydney. followed in by Canberra. And then Melbourne is down here. I've actually been to that one. And then Adelaide's over here. So you could quickly kind of just say there's Darwin. There's Perth here. There's Brisbane. Here's Sydney. Canberra. Oh, I forgot one. I just noticed. Adelaide is here. Melbourne's way down here. I'm going to have a hard time squeezing it in. Melbourne. And I forgot one last of the capitals, and it was right down here at the bottom. It's Hobart. Oops, sorry, Hobart. All right, good. So the next thing I'm going to do is I look at my map of Australia, and I'm going to have to, once I've put my dots down for each capital, state and national capital, I'm going to now connect my dots. So I'll just use green to connect my dots. So as I look at my map, there's a road that connects directly between Perth and Darwin. So that's good. And there's a road that connects between Perth and Adelaide. I can drive directly from Perth to Adelaide without going to any other capitals. The next thing I would do is I can go directly from Adelaide to Melbourne. I can go from Melbourne to Canberra. You can also go to Sydney from Melbourne without going through Canberra, so I can draw that line not going through Canberra. You can also go from Melbourne to Brisbane without going through Sydney, so you can draw that line there. You can go from Darwin to Brisbane without driving through any other cities. You could also drive from Adelaide to Brisbane without going through any other capitals if you so desired. You could go from Perth to Brisbane also without traveling through any other capitals. You could go from Canberra to Sydney and Sydney to Brisbane, so I can go from Sydney to Brisbane. And I can go from Canberra to Sydney. You can also cut from Canberra directly up to Brisbane. Brisbane's got a lot of degrees to it. And I think that's looking good. How we can also go, I forgot Adelaide to Sydney. There we go. Adelaide to Sydney. It'd be nice if I used a ruler, right? And I think we're looking pretty good. I'm just going to take 1 second and re-accentuate where my vertices are because they've now all been scribbled over. So there's Perth, Darwin, Brisbane, Sydney, Canberra, Melbourne, Adelaide. So the first question I could ask you is this a connected network diagram? And the answer would clearly be no, because we have we have Hobart down here at the bottom. Hobart that is not connected to our others because it's obviously an island. And if this is a road network map, it's obviously there are no roads that go from Hobart that connect it to. So it's a not connected diagram. That's good to note. The other thing that you could look at is it possible to drive from Perth to Sydney directly? And so as I look, there's no connecting road directly from Perth to Sydney. So if I was going to go from Perth to get to Sydney, I would have to go here through to Adelaide, and then I could get to Sydney. So again, there's not a direct road from Perth to Sydney because I'd have to go up. Again, watch this one. Another example would be if I want to go the northern route and go up, over, I'd have to get to Brisbane and then down to Sydney. So there's not a direct road between Perth and Sydney. And as a result, there's not a direct network connection between Perth and Sydney. So I think that's important to kind of point out. Proportions of the network diagram do not always have to match. You can see that I have the general idea, but my spacing is probably off a little bit. Melbourne and Hobart should be probably closer together. I don't really have Hobart well oriented, but it's not a terrible example. So you can use network diagrams to represent tables as well. So if I have a bunch of students who work together on different math problems, I can draw a network diagram to show me kind of how that works. So really quickly, the nice thing about this question when they made it is they use the letters of the alphabet. So we'll let A represent Alyssa, B represent Bo, C represent Claire, and D represent Darcy. So you go A, B, C, D. And then the next thing you could do is you then look at the question. So question 1, who worked on question 1? So Bo and Daisy worked together in question 1. So what you would then do is you would draw a line between Bo and Daisy to show that they'd worked in question 1. Who worked in question 2? Alyssa and Bo. Who worked in question 3? Alyssa and Claire. Who worked in question 4? Darcy and Claire. So that's one of the ways, and just by the positioning of my letters, that you can get the network to show that. They also have one solution in the textbook that looks more like an X or an hourglass. It's because they ordered theirs differently as well. They are isomorphic, so I'll just show you another way that that could have been visualized. So I'll just draw really quick. So there's A, B, and you'll notice I'll switch the position of D over here. So if I put, switch my color of my pen. D, and then I put a C right here. And if I draw my edges now, Alyssa and Bo still worked on that question. Bo and Darcy worked on question 1. Darcy and Claire worked on question 4. And Claire and Alyssa worked on question 3. And these are on 2 possible diagrams, and they're both isomorphic as well. If you take a second and you count the number of vertices, the edges, and the degrees for all my vertices, they would both be isomorphic as well. So I've drawn them to represent the same situation, which is a good thing in this situation. Next, you can also have weighted graphs. So recall that a weighted graph is a network diagram. It's a network diagram that has weighted edges. Weighted edges can be things like cost, the distance between 2 places, time, internet connection, speed. There's all sorts of different weights you can have. So that would be a quick definition of it. The question that they go through, and I will try to show you this one real quick. Just give me a second. I'll just plop it in here. All right, so in this one, here's an example of a weighted diagram. With the weighted diagram, you notice that you do have weights. Those weights would be the numbers on the edges. Those would tell you the distance. And I could ask you something like, what's the shortest distance between, let's go with town F and town C. So what's my shortest distance? I'll grab my highlighter out and we'll make it green. So I'm going to obviously going to town A or town E, I'm going to go this way just to start. And I think that that's a really good way to get started because 6 is smaller than 7. So I'm going to go this way. So the next thing is you got 2 choices. Do I want to go to town B? Oops, I'm not going to do that. Do I want to go to town B or do I want to go to town D? And what I'm looking at here is I'm looking at the weight here. So for some reason, wait, that's probably the weight for that one there. So I'm going to probably choose this path right here because 7 is less than 8. 4 applies to this edge right here. It's hard when you get lots of edges. So the next thing I'll do is I'll take this path next. I'm still trying to get to town C. So, do I want to go directly like this? Or is, this second option, a good idea? Well, 5 and 6 make 11, which is way more than 5. So that's probably unlikely. So then I finish off by looking at my distance. I've got 6 plus 7 plus 5. 6 and 5 is 11 plus 7 is 18. So it's going to take 18 units, 18 hours, 18 minutes, 18 kilometers, 18 miles. But the shortest distance I could find was 18 to get from A to C. And that would be a quick and easy way to use a weighted diagram. Finally, you can get and make weighted graphs from tables. Let me pop in one last table. Boom, graph. Okay. So when I looked at how they got their answer, I don't know how exactly they decided to put C directly in the middle. I don't know if it's because as I looked at the graph, C had the most amount of connections. As I read across, it has 1, 2, 3, 4, 5 different suction points. So I don't know if it's because there's those 5 different suctions. They decided to place it in the middle because there's many suction points. But when I did this myself, I started by just writing the letters. So I went with A, B, C. I tried to place them out nice and evenly around. D, that was a really nice circle. D, E, sloppy E to follow it up. E, F, and G. So I positioned my dots nice and clearly around. I then started connecting my vertices. So in the table, I looked and I saw that, B is connected to A as 32. Took a little bit more room in my notebook to do this. I then looked at A is connected to C. So like as I did them, I just scratched. So just make sure you're scratching them out as you do it. I can't get some of the ones in the top row just because my pen doesn't work up high. So next I'm going to look at AC. And A is connected to C by 15. So the next thing I'm going to do is connect them with a 15. And that takes care of that. I'd scratch out the other one, but I can't reach up top. And then I see that A is connected to D with a 20. And this is where things get messy. I forgot to also write the value of 15 between A and C. So I'll just add that in. This is going to get really messy on my stylus. I might just interrupt myself, take a picture of my work and insert it in. But I basically just continued doing this. So then once I'd done the whole row, I then went to BC. I saw that BC didn't have a connection. I wrote in BC's connection. I was a little bit neater in my notebook. When I did this and I saw BC was 30, I cancel that out, or I cross out that. I then do BF. BF's connection is 18. So this is where I'm going to just stop. This is going to get horribly messy. I'm going to connect in or attach in my my actual work. So I'll just take a picture of that and insert it in. Just give me a second. So this is the picture of what I drew in my notebook. It's a little bit neater. I'll kind of use my pen to annotate over top of it. So some of the questions they ask are weighted diagram represent the table. I've done that. D says, what's the total weighted path from A to E via BCG? So they asked, and I kind of like to write this out. So they said, what's the weighted graph from A to E? From A to E, but you have to go through B. And then you have to go through, after B, you go through C. After C, you go through G. After G, you go to finally E. So they said, what's the weighted path total from A to E via B, C, and G? So you see I've inserted B, C, and G in. The next thing I'll do is I'll start my path. So I'm starting over here at A. It's 32 plus 30. C to G, where's G here? C to G, and that uses, and this is where you got to try to draw things neatly or else it's going to get kind of messy. C to G, I'm just making sure of my work. Yeah, that's 24 right there. So from C to G, and then finally G to E is 45. So I went like this: A to B, B to C, C to G, and G to E. If you add these up, 32 plus 30 plus 24 plus 45, I believe that gets you to the grand total of 131. And whatever our units are on that, kilometers or hours or meters or whatnot. All right, I hope this helps you understand how to draw network diagrams. It's a long video. Hope you enjoyed.